Hello students, welcome back to Organic Chem-Verse. Many of you have requested me to solve questions which will be helpful for your upcoming JEE Advanced exam. Therefore, I have chosen these 5 questions which will cover at least 20 to 30 subtopics from organic chemistry. You can also try solving these questions on your own. Pause the video, solve it, and then look for the solution. If you are stuck somewhere and if you still have questions, you can always ask your queries in the comment section. So let's get started. In the first question, we have a haloarene attached to an acetal and it is treated with magnesium ether followed by ethanol and hydrolysis. So what will be the final product? So whenever we have acetal, upon hydrolysis, we know that it's going to form an aldehyde. So just look for the options where we have an aldehyde, A and D. So the answer has to be either A or D because in C it is remained as it is, not possible. And here it is an acid. So there is no oxidizing agent. So you can rule out C and B. So how to decide between A and D? For that, it's better to write down the sequence of reactions. So whenever we have haloarene or haloalkanes, so when it is treated with magnesium, the magnesium will get inserted between the carbon and halogen because that is the polar bond and it is forming MgBr. And what is this Grignard reagent? You can see that here the carbon is electrophilic. The moment magnesium comes here, it will become nucleophilic. So what do you call this as? Umpolung nature. Umpolung refers to a German word wherein you are changing the polarity from positive to negative. Because carbon is negative here, now it can act as either nucleophile or a base. How to decide that? Depending on what reaction condition we have here. It is ethanol. Now, ethanol, is it an electrophile? No. It is a weak acid. Because it is a weak acid, it will react with the Grignard reagent and here it is acting as a base. So the reaction is between acid and a base. So you can see the oxygen will gain negative charge and this will become positive charge. The negative will abstract the proton and hence you are going to get a proton over here. What about this group? No change here. This acetal will remain as it is. What is the last step? Hydrolysis. Whenever we have an acetal, right, upon hydrolysis, what we are going to get here, as I told earlier, it's going to form an aldehyde. What about this one? It's going to form a diol. That is a byproduct. Don't worry about that. That's a byproduct. So this is our main product. So what is the final product we have? Benzaldehyde. Therefore, the final answer is option D. Students, just summarize what we have learned here. So we have a beta-bromobenzaldehyde which is converted to benzaldehyde. So for that, what is done? First, protection of the aldehyde. Why protection of the aldehyde is important here? Because when you do prepare the Grignard reagent here, there is a possibility that that Grignard reagent will react with the other molecule having aldehyde. So in order to avoid this, we do protection. The protection of the group and then carry out your favored reaction. What was our favored reaction? Removal of this bromine and we are substituting there by the hydrogen. So there is no direct step here. The hydride attacking here and making this bromine leave the molecule will not happen in one step. So for that what you have to do, make it a Grignard reagent, treat it with either ethanol or simply by the water. So then what happens? You will get the hydrogen here and then deprotect it like this. So what all topics we have learned here? Protection, deprotection, hydrolysis of the acetal, Grignard reagent acting as a base or a nucleophile. So these many things we have learned just from one question. Now let's see the second question. For the second question, an aromatic compound A with the molecular formula C7H6Cl2 gives AgCl on boiling with alcoholic AgNO3 solution which will yield C7H7OCl on treatment with NaOH. That means what? AgNO3 followed by NaOH will give this organic compound and the byproduct is AgCl. So when this AgCl white precipitate will be formed, so remember whenever there is a halogen attached to the aliphatic chain. Okay, so now when this A upon oxidation gives monochlorobenzoic acid. So this oxidation means what? Maybe the reagent used is like KMnO4 in alkaline medium. It's forming monochlorobenzoic acid. But what is the position of chlorine? We don't know, and that is the question here. So in that case, what you can do? You can simply write like this. Chlorine can be either on ortho, meta, para. This upon nitration will give only mononitro product. This tells us that chlorine is preferably at the para position. How so? Remember, if it's forming mononitro product, that means what? The reactant must have more symmetry. Among ortho, meta, para, para is considered as a molecule with more symmetry. So with this much information, you can tell that option A could be the right answer. But we can verify that by writing the reactions. If you consider option A as a reactant, so this is para-chloro benzyl chloride. So when it is treated with AgNO3 followed by NaOH, this bond will get cleaved and it's going to form benzyl alcohol like this. And its formula is what? C7H7OCl. And what happens to this chlorine? It will precipitate as a white solid like this. Now, when it undergo oxidation, this one, right? So say suppose a strong oxidizing agent like KMnO4 in basic medium. First, it will convert it to benzyl alcohol, which upon oxidation will give the benzoic acid like this. And it is parachlorobenzoic acid. This upon nitration, what we are going to get? See, COH is a meta-directing. What about this? This is orthopara. Para is already blocked. So where it will go to? Ortho. So with respect to this, meta is this. With respect to this, ortho. Therefore, you are going to get only one product like this. Therefore, this statement will hold good for option A. Hence, this is the final answer. Say, suppose if you would have taken this, when it undergo oxidation, here it will form carboxylic acid. With respect to this, the meta position is this. But with respect to this, ortho and para. So what happens here? You will get multiple products, not possible. Similarly, here you will get COOH. With respect to this, meta is here and here. For this, ortho and para. So you will get two products at least. So not possible. For option D, this is not obeying the first and second statement itself. So not possible. So you can even eliminate this option in the first step itself. So this is how you have to solve this question using the reactions of haloalkanes, haloarenes, electrophilic substitution of benzene ring and oxidation. So many concepts in just one question. For the third question, there are series of reactions given. In this scenario, it's better to identify the structures of A, B, C and then choose the correct option rather than eliminating the options. What is the first reaction? It is a reaction between a ketone and hydrogen cyanide. So cyanide acts as a nucleophile and the ketone will undergo nucleophilic addition reaction. Where did you learn this? Aldehydes, ketones and carboxylic acid. So what will be the structure of the product? It is a cyanohydrine. Therefore, you can write directly like this. So this is product A. When this A is treated with lithium aluminium hydride, a strong reducing agent which will furnish 4 moles of the hydride ions. First, it will react with this alcohol and then it will reduce this nitrile to primary amine. Where you have learned this preparation of amines from the nitriles. And upon hydrolysis, what we are going to get here, the final B product here is, you can see this OH will remain as it is upon hydrolysis. What about here? A primary amine. Complete reduction of nitrile to amine. And this methyl will remain as it is. So what is this? Product B. Now, the last step here is, it's a diazotization. Diazotization because NaNO2 with H2SO4 will give us HNO2. So it will convert this NH2 to diazonium salt. But since it is aliphatic amine, these aliphatic diazonium salts are not stable. And what it will form? A carbocation over here. If it is aromatic amine, it would have been stabilized by benzene, but here it is not possible. Hence, we are getting a reaction intermediate carbocation. Now, what happens? Because we have an alcohol here and there is a carbocation, this will undergo ring expansion. How do you write that ring expansion? You see, when the bonding electrons are given to this carbon, this will become pentavalent. It cannot withstand. It has to break the bond. Where it will break the bond? Here. Since it is breaking the bond here, this carbon will go and attack this CH2. Hence, there is a ring expansion from 5-membered to 6-membered. So how do you write the product? Very simple. You write down this as it is. You write down a 6-membered ring and look at this carbon attached to benzene, benzylic carbon. That is the one which is forming a ketone here. And what happens to this carbon? It is attacking here. That means CH2, CH2. So this will be our final product. And where do we have it in the options? Check now. Look at this option B. This is 5-membered. You can eliminate that. You can see B and C are very close. Both of them are in fact isomers. The position of the ketone is different. Here it is benzylic, here it is non-benzylic, but we got this as a final product. So what all topics we have covered here? The reactions of ketones, conversion of nitriles to amines. So this is similar to Pinacol-pinacolone rearrangement. You have to remember that it's a Pinacol-pinacolone kind of rearrangement. You have an alcohol which is converted to a ketone. Hence, the final answer is option B. So in the fourth question, you have to arrange the given molecules in the decreasing order of their nucleophilic substitution reaction. What is nucleophilic substitution reaction? Here, since all the molecules are aromatic in nature, we are discussing SNR mechanism. Say suppose on benzene ring, if there is a halogen like chlorine, when the nucleophile attacks like hydroxide, methoxide, ethoxide, when it attacks this carbon, the chlorine will not act as a good leaving group. Why so? Because the lone pair of electrons present on the chlorine will exhibit plus effect, which makes this carbon-chlorine bond as a partial double bond. Therefore, when the nucleophile attacks, this bond is difficult to break. That means the order of reactivity for this molecule is less. So to increase the order of reaction for such haloarenes, you can introduce electron withdrawing groups like aldehyde, acid, nitro groups. Look at all the options. We have nitro in 3 of the options. Molecule 2 and 3 have benzene as an aromatic molecule, whereas in option 1 and 4 we have pyridine. Now, does it make any difference with respect to nucleophilic substitution? Yes, it does. How so? Pyridine will undergo nucleophilic substitution better than benzene. Is it so? Because of the heteroatom nitrogen. Nitrogen is an electron withdrawing atom because of its electronegativity. So because it withdraws electron through minus I effect, it decreases the electron density. If it is decreasing electron density, then it is activating the molecule towards the nucleophilic substitution reaction. Remember, if there is any electron withdrawing group, so there is an electron withdrawing group within the molecule. So it decreases electron density. Therefore, it increases the SNR order of reaction. So from this, you can say that molecule 1 and molecule 4 are already activated towards the SNR reaction. Compare 1 and 4 now. There is a nitro group. That means what? It is still more increasing the order of reaction towards SNR. Therefore, 4 should be the highest. Where do we have 4? Option C and D. And you can see in both the cases 3 is the least. Why 3 is the least? Because whenever we have electron withdrawing group, it has to be either on ortho and para position. Only then it will make this chlorine to leave as a good leaving group. Since it is at meta, so you can see that the third molecule is at the end. Now the competition is between 1 and 2. So how do you decide between 1 and 2? As I told you, the pyridine is always more reactive than benzene, irrespective of the position of the chlorine over here. Therefore, 1 will be more reactive. So where do we have 1 as more reactive than 2? It is in option C. Therefore, the final answer is C. For the last question, you have to identify the correct product with their reactions. The first reaction is a simple nucleophilic substitution reaction. See, although we have 3 chlorine here, there is a neighboring group effect here. The oxygen will help this chlorine to leave the molecule, and then what happens? The ethoxide will attack the same carbon. Therefore, the nucleophilic substitution happens only on this carbon. Don't worry about the stereochemistry of the product here. The question is, will it be a monosubstituted product or di or tri-substituted? So it's only monosubstituted because this oxygen is helping this chlorine to leave the molecule. Hence, this is a correct statement. Let's check the second reaction. Here, again it is a nucleophilic substitution. Where will it happen? On the benzylic carbon or this carbon? So whenever there is a benzylic halo compound, it can leave the molecule easily and form a stable benzylic carbocation, which will be stabilized by the benzene ring resonance. Hence, the nucleophilic substitution happens on the benzylic carbon, not on this carbon. Hence, this is a wrong option. Now let's see for option C. So we have a benzene attached to an aliphatic cyclic chain. The reaction is not happening on the benzene ring. It is happening on the side chain wherein the bromine is substituted by ethoxide and there is a rearrangement. So when the rearrangement happens, the methyl is supposed to come over here. Why so? Because when bromine leaves, it's going to form a carbocation over here. And there is a methyl shift, 1,2 methyl shift, and the carbocation formed here will be tertiary and ethoxide should attack over here. So this part is correct, but the methyl is missing from the product. Hence, this is also a wrong option. Now let's check for the last one. So whenever there is a bicyclic compound, just keep in mind about the Bredt's rule. So the Bredt's rule says that the double bond is not possible on the bridgehead carbon. So whenever you have bridgehead compound like this with 8 carbon or less than 8 carbon, the double bond cannot form over here, right? Or the double bond cannot form over here or here. So anywhere there is a bridgehead carbon, so it's not possible. Why so? Because whenever there is a double bond, that should be planar. In bicyclic compounds like this, the double bond cannot be planar when it is on the bridgehead carbon. But is there double bond possible on these carbons like this or here or here? Yes, this is very much possible. Hence, since it is alcoholic KOH, it is undergoing elimination but not substitution and the double bond is formed over here. So this is acceptable based on Bredt's rule. Hence, this is a correct statement. Among the given options, A and D are correct. So what all topics we have here? There is a nucleophilic substitution and there is a neighboring group participation in the nucleophilic substitution. And then we have benzylic carbocation, its stability over here. And here we have a nucleophilic substitution with rearrangement like methyl shift. And then last one is bicyclic compound, Bredt's rule, elimination. So this is how you have to solve comprehensive questions so that you will be ready for your upcoming exam. If you still have any questions on this, you can comment your queries in the comment section. In the next video, I'll come up with more and more questions. And don't forget to subscribe the channel. Thank you.